One person was apparently worried that there might be a dress code in Trinity College. There is. You will discover there a large number of people wearing dark suits and bowler hats. Whatever you do, do not dress like that. These are the college porters, which I think is best translated into American, at least, as the campus police. And they are there to help you if you get lost. Otherwise, just come dressed as a string theorist.
Okay, thanks, Malcolm. The first speaker of this last session is David Berenstein, and he's talking about N=1 dualities and the dynamics of brane anti-brane systems.
Okay, it's a pleasure to be here, to have the opportunity to talk about this recent work with Mike Douglas, which came out about 2 weeks ago. So this is fairly new stuff. And then let me give you an idea of some fairly old subject in supersymmetric gauge theories, where Seiberg discovered an infrared duality between two QCD-type theories, both with the same number of flavors, NF, but with very different gauge groups. And the gauge groups were SU NC and SU NF minus NC. And these two theories, which classically look completely different, are supposed to be equivalent as quantum theories in the infrared. So this discovery connects two quantum field theories, which at the classical level don't look anything at all like each other. So a popular way to derive these dualities is to try to embed the story in string theory and use some sort of geometric engineering. So you can realize the brane's configurations and the field theories geometrically, either as suspended brane constructions like Hanani-Witten type and the work of Elitzur, Gideon, Kutzasov, also as D-branes wrapping cycles in a Calabi-Yau manifold, like the recent work of Kashasov, Yol, Interrogator, Katz, and Waffa. And there's also orbifolds in the resolutions, and especially the recent work on toric dualities, which show some relation and some generalizations of Seiberg duality for different theories. The main drawback of all of these explanations is that they have a hard time explaining in a satisfying manner the superpotential that is necessary to make the dualities work. And the objective of this talk is to actually give you some formalism that at least allows you to say something about the superpotential at a classical level and that tries to derive the duality in some sense in a classical setup so that we can actually understand where these superpotentials come from. So the outline of the talk is as follows. I'm going to theories as holomorphic branes in a Calabi-Yau manifold. I'm going to show some relation between central charge and gauge couplings that will let me make some statement about what Seiberg duality should be in this setup. I'm going to explain the duality as some sort of change of basis of fractional branes. And then I'm going to go to some length to explain a little bit about how you fit these into brane categories and how to compute things with exact sequences and homological algebra. And then I'm going to go back to Seiberg's original example and try to explain that in as much detail as possible, considering the time constraints. And then the last part will be to show that the superpotential of the dual theory in the Seiberg duality actually comes from understanding the tachyon dynamics of brane-anti-brane systems. And hopefully that should do it. So first, the way I'm going to construct field theories in a geometrically engineered manner is to wrap branes holomorphically on some cycles. And I want to understand these as wrapping linearly independent cycles so that wrapping a brane on one cycle cannot be considered as a sub-brane of some other brane that I have in my configuration. And then I'm going to label these branes as BI. And I can construct a theory by wrapping branes in some form. So this is a brane which is wrapped Ni times around the cycle associated to the brane BI. And the idea is that this is the field theory I want to understand. And then the D-brane, each D-brane in the holomorphic setup is associated to some coherent sheaf on the Calabi-Yau M. And the massless spectrums of states between D-branes, which is the field theory data that you need, the massless string states correspond to the field theory quanta are given by calculating something called X groups, which are just holomorphic forms twisted by some product of the two coherent sheaves or the bundles associated to them. And this, in the topological string theory language, the Q is called the ghost charge. And this is just the degree of the Q form that you have to associate to it. And then the assumption that the cycles are independent translates into having no holomorphic forms between different linearly independent cycles. So the X0, which is the homomorphisms between these branes, is 0 for I different than J. And this category of sheaves has some duality functor, which lets you express all of these H0Q in terms of H0I with I less than D halves. So in the case of a threefold, you will only have X0 and X1. And if you take into account the GSO projection, that means you include the directions that are transverse to a Calabi-Yau in the setup, then the X0, the homomorphisms, combined with the GSO projection become the vector multiplets, and the X1 become the hypermultiplets, or the matter multiplets of the theory. And then with these conditions, the gauge theories will have a gauge group product of U and I, where Ni is the wrapping number around each cycle. Now, the important note that I want to get across is that all of the holomorphic data of the field theory is contained in the twisted B-model topological string theory. And the topological open strings are the field theory degrees of freedom that you need to construct the field theories. So most of the information that we're after in the duality, which is holomorphic information, is contained in the topological string theory. And that will allow us to actually compute things explicitly. The topological string theory correlation functions are going to give us the superpotential. So the data of the topological string theory, the branes wrapping the cycles, and the topological correlation functions will determine the holomorphic data of the theory. And the rest of the data, which is how do we choose the cycles that we wrap branes under, is determined by Kähler data. So the choice of bases of cycles that we need is going to be determined by the things that are not protected by supersymmetry. And then the idea is that the Kähler data will determine whether holomorphic field configuration is actually a BPS state and gives rise to some supersymmetric vacuum or not. So the main setup is that you treat the D branes inside the Calabi-Yau as if they're weakly coupled objects. And if I wrap some cycle in the Calabi-Yau in the type 2B theory, and I consider the gauge theory associated to that, I can also consider the type 2A version of the same object, where I wrap the brane around the same cycle, but which is now a point in the transverse directions to a Calabi-Yau. And this object, if the original theory has a supersymmetric vacuum, corresponds to a BPS brane in an n equal to 2 theory, because the compactification of the Calabi-Yau has an n equal to 2 supersymmetry, and therefore there's an associated central charge. And the BPS bound relates the tension of this brane to the norm of the central charge. And in the gauge theory limit, one has that the gauge coupling of the associated brane is roughly equal to the norm of the central charge up to normalization. And then this is equal to the volume of the appropriate cycle in the Calabi-Yau manifold, which is determined by the Kähler data. And the Fayet-Iliopoulos term of the same gauge coupling is roughly the phase of the central charge. The central charge is complex, it has a phase, and the Fayet-Iliopoulos term associated to this gauge group is exactly, well, in the field theory limit where all of these phases are roughly aligned, this Fayet-Iliopoulos term controls the imaginary part, the phase of the central charge. So the idea is that two branes will be mutually supersymmetric if their phases coincide, and if they're not supersymmetric, then you consider that supersymmetry is spontaneously broken. So Seibert's duality usually tells us that we have to go to strong coupling in one theory to understand the dual theory. And going to strong coupling in the classical level corresponds to going through zero volume of the cycle. So we turn this into the condition that the central charge has to vanish. And then the idea is that to understand the dual theory, we need to analytically continue around the singular point, which in the conformal field theory would lead to a bad conformal field theory because it has some cycle of zero volume, and some d brane is massless at that point. So the conformal field theory would be singular. But the point is that we are going around it. We can avoid this region going around the point z, or the central charge vanishing, on a path where the central charge is, well, much bigger than 1 in the Kähler moduli space. And what we're really doing is changing the phase of the associated object by pi. So the central charge would take z of the brane E to something which is in the opposite direction, which becomes anti-BPS with respect to some other branes. So we have some collection of branes BI that are mutually supersymmetric at some point in Kähler moduli space, and I'm moving Kähler moduli space. Then, in the end, at the end of the motion, in the classical moduli space of the string theory, it will be the anti-brane of the brane E, which is mutually supersymmetric with the branes BI. So we need to sort of change our basis from branes to anti-branes. And we need to understand how this is going to work on the string theory level. And if you think of a string theory or a field theory which is related to this configuration, then you cannot describe this theory as a supersymmetric field theory after we take the central charge going negative. Because in this case, the supersymmetry breaking is too high. It's at the string scale. So we can think of this collection of BIE that we have as some sort of choice of basis of fractional branes. And now, to write something that makes sense as a supersymmetric theory on the new point in Kähler moduli space, we want to change our basis so that the new branes which we write are actually mutually supersymmetric with respect to each other. And the question is what types of branes we're going to take. So we're going to just dualize one node or one gauge group, and this takes the node E to its anti-brane. Now, we can consider, for example, bound states of these branes BI and E. And the idea is that these bound states, if they're supersymmetric, we can actually continue them around the singularity. And these bound states will have smaller central charge at the end point in Kähler moduli space than the original branes BI. And the reason is because the central charge of this object will have some positive contribution from BI and some negative contribution from E. So this object will be more basic than the brane BI itself. The brane BI itself will be interpreted as a bound state of this new brane, B hat, and E bar. So this is the idea for the duality, that we need to make this change of basis where we take these bound states and we write the theory, the original brane configuration, the original brane charge, in terms of some new bound states. So the idea is that the brane theory, this one, will not change, but the expression in terms of the basis will. So I go from BI or NI times BI to NI times BI hat. There should be a hat over here. And then the BI hat captures some branes of type E, and then we need to compensate the charge with anti-branes, and this is the number we obtain. And you see here something that contains the number of flavors, because these branes, the branes BI, will give rise to flavors for the brane E when these two branes intersect. And then you change from number of colors to minus number of colors. So this is the switch that you expect from the duality. There's some shift from going to NC to minus NC, and this shift depends on the number of flavors you have in the theory. So what's the idea? The idea is that you want to deal with branes and anti-branes on the same footing, and you're in the topological theory, so that's going to be easier. And the way you introduce anti-branes is that you want to think of a brane annihilating its anti-brane via tachyon as a process that is allowed in the topological string theory, and that this object has no content in the topological field theory. So the way to do that is that you replace coherent sheaves by complexes of coherent sheaves, and to some extent the brane represented by the complex is the cohomology of D. So this is a complex. These are some maps between the coherent sheaves. And the cohomology of D is roughly what you call the brane configuration associated to the complex. So the idea is that when you have objects that are shifted by some amount in this complex, they can be interpreted either as branes or anti-branes depending on their position inside this complex. So this object over here represents brane-anti-brane annihilation by tachyon condensation. And you can also represent a bound state of branes, B1 and B2, for example, as a middle term in an exact sequence. So this object over here has some sort of tachyons with B1 and B2 that if you condense, you get 0. And the idea is that this state B is roughly some bound states of B1 and B2. So this lets us understand how to build these bound states that I was talking about. And then when you have these sort of short exact sequences, then there's an associated long exact sequence for these X functors. This is just a standard computation in homological algebra. And the idea of these exact sequences is that if you know the constituent pieces that make up a brane, and you know how the brane is deformed from the direct sum of B1 and B2 to form B, then you can actually compute all of the information that is necessary to obtain the spectrum of strings that begin in B and end at some other brane M. So if you do this in coherent sheaves, this is well known. You can also do this in the case of complexes of sheaves, and you get something which is roughly of the same form, except that now the XQ has some extra shift, Q plus N minus M. You interpret this shift as some contribution from the endpoints of the string to the ghost charge of a string. And the idea behind this shift is that when we break supersymmetry by some change in the phases, by adding Fayet-Leopoulos terms, the bosonic partners of the fermions will get an additional contribution to their mass, so the bosons and the fermions will not be degenerate when they vanish. And this extra contribution that makes them more tachyonic or less tachyonic is governed by how much we broke the supersymmetry between phi A and phi B. So if you have two branes that differ by phase or by a shift of plus minus 1, they are the ones that correspond to a brane and an anti-brane, and they have the opposite phases with respect to the central charge. And with respect to this ghost charge, they also have different masses. So let's go back to Seibert's original example. We start with a theory with branes B1, B2, B3. I'm going to dualize brane B2. I'm going to call this theory B, N1, N2, N3. I just labeled the gauge groups. Anomaly cancellation requires that N1 is equal to N3 for the node B2. But since we're doing classical arguments, we will ignore that for the time being. And then the question is, what are good bound states that we can form that make up the new basis? So the new bound state should be such that when you look at an individual bound state of those, they should lead to a U1 gauge group. And the bound states that you can form with that property are these following ones. Brane B4, which has content 1, 1, 0. Brane B5, which has content 0, 1, 1. And brane B6, which has content 1, 1, 1. And to form each one of these bound states classically, you need an obvious choice of D terms to obtain supersymmetric vacua. So changing these D terms is changing the phase of the associated brane. And if we're interested in dualizing B2 so that we take the Fayet-Leopoulos term of this brane B2 very, very large, then we can keep B1, B5, and B2 bar to make the new basis, but we are not allowed to keep B4 because the brane B4 does not give rise to a supersymmetric vacua for this choice of Fayet-Leopoulos term. If I would have made the other choice of convention, Z2 less than 0, then the one that would not be allowed is B5. So there's some asymmetry between the incoming and the outgoing arrows, and this asymmetry is correlated to how I choose the signs for the D terms. So when I write the theory of brane B in terms of the new branes, then this is what I obtain. I obtain N1, branes B1, I obtain number of flavors, no minus number of colors of brane B2 bar, and then I get N3 type of brane B5. And this is exactly what you would expect from the dual gauge theory predicted by Seibert. You go from number of colors to number of flavors minus number of colors. So now let us explore the matter content. You just follow the long exact sequence of X, and then what you obtain is that if you consider, for example, the brane B5 plus B1, this is the one that's not associated to the dual gauge group. These are sort of spectator branes. Then in the dual theory, we expect to see a meson field associated to these gauge groups. And this meson field will come exactly from the strings that stretch between brane B1 and brane B2. And B2 is part of B5. So there were some quarks that go from here to here. And then these fields are going to be the meson fields of the dual theory. You can also understand what happens to the field content associated to the brane's B2 bar. You just follow the exact sequence, and you shift by 1 because you have to remember that there's this shift in the ghost charge of the fields when we pass from a brane to an anti-brane. So X2 of B2, B1 will become X2, or X1 of B2, B1 will become X2 of B2 bar B1, and then Serre duality, you can dualize these and it becomes X1 of B1, B2 bar, and that essentially tells you that since you have this shift from 2 to 1, you have to reverse the arrows in the quiver diagram, but essentially you get the same group. You get the same number of flavors because this group counts the number of flavors between the branes, and then this gives you the same number of flavors but with the opposite orientation. And then doing the same long exact sequence for the third pair of branes gives you the same type of objects as you had before. You reverse the arrows again, and then you shift by 1. And then when you look at this spectrum, you've produced exactly the spectrum of the dual theory. So here's a computation for consistency. If you have the dual theory now, you can try to do the same or the inverse duality procedure, and you can build a new brane between, there's an error over here. There should be a brane B7 over here. I tried to build a bound state B7, and the idea is that now in the dual theory there is a superpotential. In the superpotential you're going to get some connecting homomorphism here that will eliminate the double dual mesons. So this term is actually part of the superpotential. Wait. Oh, I got confused over here. When we do the B2, when we build the brane B5 out of B2, this connecting homomorphism here is not from the superpotential. This is actually from X2 to X3. This is a connecting homomorphism that details the Higgs mechanism. So when you give a VEV to one of these arrows to build a bound state, then you have to take some gauge field, X3 is dual to X0. X0 was the stuff that corresponded to a gauge field. And the gauge field needs a particle to become massive. So in the topological field theory, we only retain the massless modes. And this connecting homomorphism between these lines is actually the thing that takes care of the Higgs mechanism. So the Higgs mechanism is encoded in these homological algebra calculations. And this is just a matter of however many fields we have up here. And this is just the counting of linear algebra. And because we want to understand the anti-brane, we need to do a shift in X from X0 to X1. And then this shift from that we get over here from X03, from B2, going to the anti-brane, produces the tachyons. So these are the gauge fields. The tachyons are related to the gauge fields for a brane-anti-brane system. And then now for the self-consistency check, we have the two theories. We have the second theory, and we want to build a double dual theory. If the theory has a superpotential trace QM Q tilde, as is expected by duality, then we can produce again some long exact sequence, and we get this connecting homomorphism that details the superpotential. We still need to prove that this is the superpotential. So the idea is that the two types of connecting homomorphisms, x2, x3, and x1, x2, are essentially the same thing in the homological setup, but this is gauge and superpotential dynamics being treated on the same footing. Now, to understand the tachyon superpotential, let me add an extra configuration over here. Then I need to include terms in the potential that take care of the tachyon dynamics. Brane, anti-brane should eliminate all of the possible fields. So there's going to be two terms, trace of T, Q, Q tilde bar, and trace of T tilde Q, Q bar. So if you think in terms of this diagram where you have branes and anti-branes, B2, B2 bar, and B1 and B3, then the tachyon potential gives you some triangle over here, some term in the potential that you need to have in order to eliminate these arrows when you condense this tachyon. And there's also a similar potential term for this triangle. So these two terms are going to give us the dual superpotential. One of them takes care of when we give a VEV to the field Q tilde to form the bound state, then, or actually this is Q. When we give a VEV to the field Q tilde, then we make Q massive, or Q bar massive. And when we give a VEV to this tachyon, then we make the other two fields massive. The end spectrum of the dual theory comes from the leftover matter that we see in the field theory, and we have the tachyon, this tachyon over here, is part of the spectrum of the dual theory, the quarks, and then we get this new quark over here, which comes from this arrow that is required for the field theory to make sense. I'm out of time, but the idea is that this is the story. And the outlook is that we have seen at least how the tachyon generates the right superpotential for the dual theory. We have shown how string theory arguments allow really to derive the superpotential from first principles. And then in principle, one can find new dualities. And the question is, well, how can one go beyond?